This is our premiere episode of Physics Frontiers, and we've got something really special for you. In fact, this is something I've been looking for since I was 10 years old, an alternative theory to gravitation expressed in the language of engineering and quantum theory, rather than the tensor calculus equations of Einstein's general theory of relativity. And yet it makes nearly identical predictions to Einstein's revolutionary theory, with some subtle exceptions that lie just beyond our finest astronomical observations. Though, as we'll see, that's about to change. The theory is called G4V, or four-vector potential gravitation, and its discoverer is Dr. Carver Mead, the Gordon and Betty Moore Professor Emeritus of Engineering and Applied Science at Caltech. Jim, let's start there. What do we know about Carver Mead?
I don't know anything about Carver Mead. I didn't realize what I knew about Carver Mead until I saw him at the end of the talk here put up a book. I'm pretty sure that book was Collective Electrodynamics.
That's right.
Which is a book that he had written to try to express the fundamentality of the vector potential in the theory of electrodynamics. And he did that basically by talking about quantum mechanics, the vector potential, and superconductors. At least that's what I recall from reading it, which has been at least a year, probably about 3.
Oh, I'm glad you read it, because I've only dipped my toe in it, and it's a pretty fascinating way to reconceptualize electrodynamics. And we're so used to looking at it from the classical Maxwellian perspective of electrical potentials and magnetic fields that to have him go and reinterpret the entire thing was pretty interesting and I think really elegant.
I mean, I didn't really see that as too great a reinterpretation. When I was reading it, at least, it seemed to me that it was mainly just putting one thing at the forefront, which probably isn't too bad. I mean, considering what we've been looking at in the main podcast,
Physics FM.
Yeah, on Physics FM, that vector potential is very, very important. It's the way that it's the way that electricity and magnetism kind of get put into quantum mechanics.
Yes.
And therefore it should have a very, very strong claim for centrality.
Yep. Fundamental.
Yeah, so I mean, I think that's a pretty reasonable thing for him to do. The main problem I have with an idea like that, with like the vector potential, is just I don't really know how to say that this is the vector potential, right, at such and such a point. You know, I know how to say this is going to be the scalar potential, right? So when you're doing a lot of things like electromagnetic calculations, you just figure out what you want the potential to be at different points, because you sort of control that with your equipment. You say, okay, this is at ground, so that's 0 volts. This has to be at 25 volts, and you know, all those other things. And you can sort of control all that. And then you can figure out where all the fields are. But as far as controlling that vector potential, that I don't have any real idea how to do. All I really know how to do is know how to put a current in a loop or put a magnet someplace. And those will make the magnetic field, and then I can sort of figure out something like that vector potential based on that. I think a lot of people don't do very much with it because it doesn't really do the same thing that the scalar potential does.
Right, it doesn't give you a simple force relationship.
Well, yeah, what it doesn't do is it doesn't make everything simpler for you, right? So the scalar potential can be used to find an electric field. You have this number in space, and then you can take some derivatives, and you can get a vector in space. That makes it extremely useful. You've basically taken 3 differential equations and turned them into one, and now you're very, very happy. Now, of course, the vector and scalar potentials aren't separate. I mean, they're only separate in classical physics. In relativistic physics, they're all part of the same sort of number, the same tensor. So this guy's calling his thing G4V, right? I think that stands for gravity and 4-vector or something like that.
Yeah, 4-vector potential, yeah.
So that 4-vector potential has as its time component the scalar potential of electricity and magnetism, probably scaled. If everything's in units of A, it's probably scaled by C. If you've got everything in terms of the scalar potential, I think you divide by C for the vector potential. I'm not quite sure about that.
C squared.
C squared, okay. So that would work out fairly well.
Well, now we're going to be discussing, I guess, primarily Carver Mead's discussion that he gave called G4V, An Engineering Approach to Gravitation, which you can find on YouTube.
Yeah, we'll put that in the show notes, wherever we have the show notes.
Right, wherever they will be, hopefully right underneath whatever you're looking at now. And so he went back and he looked at Einstein's papers, and I didn't even know about these papers from 1907 to 1912, after he did his work on actually the discovery, basically, of quantum theory with the photoelectric effect. He went on to gravity, and there were these papers that I'd never even heard of before, and he became fascinated with them because he was building a theory of gravitation using the engineering language of physics from that time, and he was able to basically complete the work that Einstein was doing from 1911 to 1912 and show that Einstein might have been on the right track for a working model of gravitation long before he discovered the general theory of relativity, which is more intuitive and speaks the exact same language as the work that we see in his book, Collective Electrodynamics, which speaks the language of quantum theory and engineering. So it's a fascinating lecture, about 65 minutes that he gave at Caltech. And it's really got my mind on fire because I've always wanted to see if there was another way to make the predictions that we see in general relativity using a different language mathematically, one that didn't require very sophisticated and in many ways opaque tensor calculus equations. And this model appears to me to be a lot more intuitive, but it makes a totally fundamentally different approach to the problem, because general relativity talks about gravitation as a distortion in the space-time metric in order to preserve the postulate that the speed of light is always constant. So you've basically got to twist reality in order to make our observations fit with his theory. But Carver Mead has thrown a wrench into that entirely, and he's actually saying that the speed of light physically varies within a gravitational field. And he describes phenomena like gravitational waves, which are normally modeled as ripples in space-time. He's expressing them as potential fields that simply move matter around. So instead of a gravitational wave passing through the LIGO and causing space-time to distort the length of the laser pathways, he says that no, there's actually a transmission of a field which causes the matter, like a force on the matter, and it causes matter to move relative to other matter in the area, in the vicinity, so that you can measure it. And it just I'm astounded that he's got accurate mathematical predictions out of this theory.
It is fairly interesting. First of all, of course, you should just go ahead and make a day trip to LIGO, because you've got that up on the other side of the lake.
Yeah.
You know, get a couple of cute girls to drive you, and I'm sure they'll invite you back. Now, do you remember I showed you a book once? I think I was actually trying to set that up as the next book for the main podcast, which would have been Theory and Experiment in Gravitational Physics by a guy named Clifford Will. It was a green book.
I don't remember seeing that.
Yeah, so I think while we were still cruising on that pretty well, I was thinking that maybe we could try that one. So, I mean, I had that with me, and this guy was talking about the Shapiro effect and stuff like that. What was the name of that? Shapiro delay.
Yeah.
So Mead was talking about Shapiro delay, and I wanted to see more or less what that was all about and so forth. Mm-hmm. And all that's actually covered in that book, especially because he's got maybe a decade's worth of experiments. So it turns out that's a really important thing for a theory of gravity to look at.
Yeah.
But that's the reason why I went there. But the things that I found there, I found a couple of different things. One is this 1911 paper had been used over and over and over again by people, and I'm not sure the quality of those people as far as theoretical physics goes. But from reading his chapter on testing these theories, Will seems to imply that people go back to those over and over and over again to try to try to show different things about general relativity, like showing deflection just from the equivalence principle.
Well, right, but the 1911 paper, which was titled On the Influence of Gravitation on the Propagation of Light, in that paper, Einstein had made the wrong prediction for the deflection of starlight around a gravitational body. He only got a value that was 1/2 of the actual value. And it wasn't until his, I guess, 1912 paper where he gets close enough that Carver Mead points out that he, with one extra step, if he'd taken the equation one step further than he had it in the paper, Einstein would have realized at that point that he had been off by a factor of 2, and he could have had the deflection of starlight prediction that he had got from general relativity.
Well, yeah. I mean, he's saying that 1912 paper where he starts talking about the, I guess, gravitational vector potential. He says that when he combines that 1912 paper with that 1911 paper, he can double that to make it sort of match.
It's the 1912 paper is called "Is There a Gravitational Effect?" which is analogous to electrodynamic induction.
Yes. So I mean, that's kind of interesting because that seems to be sort of a beginning for gravitomagnetism in some way. But it doesn't really seem to be that way because this Carver Mead doesn't seem to know anything about it. When somebody asks him at the very end about gravitomagnetism, he answers a completely different question about general relativity.
Yeah, but he does explain in his talk that the 1912 paper predicts frame dragging, and he talks about the gravity probe B. He talks about how there's a gravitational analogy to a charge, like an electrical charge, within a spherical shell of charge, and how if you move that sphere, that it induces motion in the charge within. And he talks about how if you rotate the sphere if this is a gravitational model now, where you've got a shell of mass and you've got a test body in the middle, if you rotate it, the mass will rotate with the shell. So he does seem to understand the concept of frame dragging.
Yeah, what I'm saying is that it looks like Mead has worked out, basically that kind of theory. But it doesn't look like he's heard about it from other people. It doesn't look like he's spent a lot of time looking at what other people have done with it. It looks like he had this idea and he just went off and worked it all out by himself, which is awesome. But it doesn't look like he's looked at all of the different issues that might arise because of that. I think it sounds like most of what he's got from as far as checking this out, comes from taking Kip Thorne to lunch.
Well, on the other hand, he's saying that this model of gravity is perfectly analogous to the electrodynamic model that he describes in his book, Collective Electrodynamics. He seems to intuitively understand that you can do everything with gravitational effects that you can do with electrodynamic induction.
Yeah, I think that's right. I think that's the basis of what he's talking about.
And that amazes me. I didn't realize. I remember one time we discussed this a little bit because, as most people familiar with physics are aware, the Newtonian equations for electromagnetism, or rather I should just say electrostatic charge interactions, is identical to the Newtonian math for gravity. And you can actually take this a step further, you can see that there's a gravito-electromagnetic analogy to electromagnetism, with everything with mass currents that are equivalent to electrical currents and all the rest. But the parallel only seems to hold true in the weak field limit, where the gravitational field is very strong and the motions aren't anywhere near the speed of light. Carver Mead's saying that using his formulas, that you get the exact correct predictions, the same ones that general relativity gives you. So I don't know how that the problem of the nonlinearity of the gravito-electromagnetism of general relativity gets resolved in his theory, but it seems to have something to do with his use of the Mach's principle and how the inertia of a body is dependent upon the other masses in the area and how they're moving. But I know that he's working on a full treatment of his theory. He seems to already have it all worked out, as far as I can tell. but because he's making numeric predictions and he's testing them against things like binary stars and their gravitational radiation and how much energy they're decaying away, and getting very fine predictions out of that.
Yeah, well, I think that's what he has to do. The stuff that he's talking about with the binary stars, the stuff that he's talking about with the slowing down of light with the Shapiro delay, those are apparently the classical tests for a gravitational theory. I should have marked them off and made a little table or something. But it seems to me that he's actually hit all of those tests.
Yes.
So there should be something where all of this is published by now, but I'm not sure.
I don't think that he's published anything on the general expression of the theory, but he has published a paper. What is it called? Gravitational waves in G4V. He published that last year. So he goes into the specific mechanics of gravitational radiation and how his prediction is very distinctly different than the prediction of general relativity. Not in magnitude as much, although there is a slight deviation there, but in the polarization, in the way that the radiation works. We've picked up one gravitational wave signal detection so far from the LIGO experiment here in Louisiana, and what we don't know is the orientation of the star system and apparently a black hole ate something and sent us a big gravitational wave. We don't know what the orientation of that system was relative to the Earth, so we don't know which one of these theories is correct. In GR, apparently, the gravitational radiation is strongest along the rotational axis of two bodies that are spiraling into each other, or even orbiting. In his theory, the gravitational radiation is strongest in the plane of that orbit. So it's off by a 90-degree angle. And we don't know the orientation of astronomical objects that far away to tell just from the gravitational radiation, but there may be astronomical observations in the future that will allow us to do that. Plus, he talks about, and I did a little reading online about it too, they're opening up a new LIGO experiment in Italy, and apparently using the one in Italy with the ones that we have in the United States, they'll be able to settle this question as to which theory is predicting the right polarization for a gravitational wave.
Was that where he was looking at the filters? He had the filter graphs at the end, right?
He did. There was a few ways to filter the data so that to make them more sensitive for either GR or G4V. And I believe there's a hybrid method that they could have used, but it requires a second observatory so that you can detect what the polarization of the radiation is. And he showed some graphs in the lecture that you'll see on YouTube about this. And frankly, it looks to me like the graphs for gravitational radiation in G4V are far more elegant in shape than the graphs that model the predictions of general relativity. Did you notice that?
No, not really.
There were these in G4V. There's the magnitude of the gravitational radiation along different angles creates a three-dimensional map of basically like four spheres around the origin. And in general relativity, it's kind of a distorted, misshapen volume that is all along it's rotated along like 90 degrees out of plane relative to G4V. And those looked kind of labored to me. I don't know if there is a kind of beauty, I think, to the mathematical predictions that he's making.
Or it could be Mathematica just likes his equations better. Yeah, he was doing that with all that weird stuff with the little point masses going up and down along the detector.
Look how much more beautiful those graphs are in G4V than they are in GR. Look at the one on the upper right-hand corner. What kind of bizarre, distorted shape is that? And that's just plotting the magnitude of the field energy at any given orientation to the bodies, right?
Yeah, I'm not really sure. The labels are very difficult for me to tell exactly what they are. And, the labels on the G4V thing sort of make sense. But they aren't the same labels as GR. GR has something like cross sensitivity. G4V has Y sensitivity.
Right.
it's hard to really compare them if they have if they're different labels. I'm not, since I don't know enough about them.
Yeah, and he is talking about not just the wave itself, but its interaction with the detector.
Mm-hmm.
And the detector consists of two arms at a 90-degree angle, and so you're going to get this kind of hybrid mathematical product of theory with the detector in that configuration. But it does seem like you've got a simple geometry for a detector, and you've got, in G4V's case, a pretty simple theory which describes gravitational radiation perfectly analogous to electromagnetic radiation. There was a question after the lecture where somebody raised a question about spin 2 waves, and I didn't really understand his answer about that, because conventionally physicists say that general relativity and gravitational waves, they predict a spin 2 radiation, whereas electromagnetism is what, a spin 1?
The photon is a spin 1 particle, and they say that the graviton would have to be a spin 2 particle.
Yeah, I don't know if he's modeling if his radiation has the same characteristics. It seems like he seems to think that they're going to be perfectly analogous to electromagnetism, which would indicate a spin 1.
But he might only need a spin 1 if he doesn't have the strange background. So now the whole thing about this theory that he's putting forward, as far as I can tell, is that it's all on a flat background, right? It's on a Euclidean space-time that he puts all this stuff into.
Right.
And so he might
right.
not need the spin 2 because he doesn't need that. He doesn't need a matrix, right? So he might only need a spin 1 particle. I don't know what more you have to do with that,
Right?
because there are only so many things you can characterize your particle with. So how would his graviton differ from a photon, other than what it interacted with, right? So
yeah, it doesn't seem like he's making really any fundamental distinction there at all. If you look at that frame at 51 minutes, where he's got the gravitational wave passing by the test particles, right? Isn't that exactly what a photon or an EM wave would do to test charges that are placed near the beam?
yeah,
like
I think
that?
so. I mean, they look like classical radiation patterns.
Yeah.
I mean, I haven't studied them in detail enough to be certain about that, but when I looked at them, they just looked like classical radiation patterns.
Yeah. I'm really thrilled with this. One of the things that fascinated me that I was hoping to get some clarification on, I was hoping you could help me with here, is he talks about, and this is what he does with his book Collective Electrodynamics too, is he goes to the superconducting solenoid, a coil of superconducting wire, like an inductor, and he runs the calculation on the inertia of each electron within the wire, and he talks about how each electron in the wire, because it's interacting so strongly, basically is a single, it's coupled completely with all of the other electrons in the solenoid, behaves as if its mass is 1 billion times greater than an electron in free space far from all other electrons. So that makes me wonder, if it's got 1 billion times more inertial mass, wouldn't it also have 1 billion times more gravitational mass?
That inertial mass, it comes from its sort of interactions with other things. Really, it's sort of the quasi-particle. It's not the real particle there. It's sort of the electron plus other things. And this wave function, and you have a collective wave function, and you have some probability of seeing something here or there, but you don't really have anything else. So all of that has a lot to do with transfers of crystal momentum and stuff like that. So I wouldn't be worried too much about it as being another extra mass, another extra gravitational mass.
Well, see, that's where I get mixed up, because when he talks about the mass of a body, say any body in our universe, he's saying that its inertial mass is created by its interaction with all of the other mass in the universe, right?
Mm-hmm.
So basically, if you increased the mass density of the universe 2 times, you would expect the inertial mass of any given body within that universe to also increase 2 times, right? Or there'd be some kind of mathematical relationship, but it would increase, right? Because there's more coupling. So I'm just thinking that maybe, so wouldn't that mean that body would have twice as much gravitational field?
I'm really not sure. It probably would not, because it's all going into this vector potential instead of the scalar potential. The general way that you're thinking about the effective mass is that you're no longer really looking at an electron when the electron is in a material. What you're looking at is sort of this electron plus. You have a pretty good idea that you can follow this one electron around, but it's also got little bits of other things that it's connected to.
Yeah, he likes to say that the momentum of an electron includes the momentum of every other electron in the universe.
Kind of. Mostly the momentum of any electron or any Cooper pair in a superconductor is connected to every other electron or Cooper pair in that superconductor. That's where this really comes in. All these other things are not going to be connected in any way close to that stuff that's actually going on in the material. So, I mean, I would look at that and I'd say that he's probably looking at something like the effective mass. I'm sure it's exactly the effective mass. That I can understand that same thing has something to do with that retardation. He's saying that he's got a sphere, right? And he's got this perfectly symmetrical sphere that's hollow on the inside, and he puts a little dot of something in the middle. Now, classically, if you don't have that vector potential, if you just have a classical gravitational field,
a Newtonian gravitational field, you don't get any induction of motion.
You don't get any. Yeah, there's no net field on anything inside that sphere. There's no net force on anything inside of that sphere. But if he has the vector potential, then when you have the motion, that motion breaks that symmetry, and there's a coupling through that vector potential directly into the momentum of particle, and that's what moves it around. I mean, that's one of the things we also looked at in the main podcast, is that this vector potential the vector potential does not go into the potential energy part of the Hamiltonian. It goes directly into the
kinetic energy,
the kinetic energy, and modifies the momentum by saying there's some sort of background something that's going on. And in this case, and in both cases, right, it's really the background everything in the universe, right, it is actually affecting the momentum. It's some sort of, I'm not sure if average is the best word, but it's some sort of average of everything else, making a kind of reference to the rest of the universe in any motion that you actually have.
I'm just beginning to think of it this way. I was just thinking of it. If you have a spherical shell of gravitational matter, and there's a test body somewhere inside of it. It could be anywhere because there's a net zero field statically all inside that sphere. And then you move the sphere, you get this induction of motion of the particle inside. But now I'm thinking in terms of inertia, and if you look at the universe as basically a series of spherical shells of uniform density, and then you move the particle inside, then there would also be that vector potential interaction with all of the shells of matter around you. So that would perhaps account for the large inertial mass that we see with matter, because you're interacting with the whole universe when you move this test body, right?
Something like that, possibly. Yeah, and I'm not sure how that actually works out, because the sorts of equations and things he gives are for very specific situations.
He's just going over the experimental evidence for GR, and he's showing how G4V predicts all of it using the mathematics of that case, right?
Yeah, so he's got this stuff that for very specific instances, and he doesn't have the stuff for more general cases.
I'm dying to see that. I want to see the whole treatment, right?
Yeah, so I'm not exactly sure how this sort of works. I guess you could try to figure it out by saying, okay, let's say I have a big sphere of charge, right? And I've got a charged particle in the middle, and I move that big sphere of charge. What happens to that charged particle in the middle? In which case, it's going to do something kind of weird. It's hard to tell, but, it should shift.
Yeah.
But it's not going to have the same kind of effect, because you're going to have the charge-to-mass ratio issue. It's going to show up because now, the mass and the charge are different things, rather than what we have in classical physics, where the inertial mass and the mass charge are the same thing. So for a particular for a particular gravitational problem, that charge to mass ratio is 1 because they're the same thing. And I think that stays this way. So when he's talking about the inertia here, he's talking about this effective mass, which is talking about moving that entire collection of things, that quasi-particle, moving the quasi-particle, shifting around that wave function rather than actually moving around a particle.
But in this model, isn't it the same thing? Isn't the coupling between a body, that your test body, and the universe around you, isn't that also an effective mass, basically, because of the interactions, because of the vector potential?
I think there's something in there, right? Because I think part of what he's trying to say is that
It's like the ultimate mathematical validation of Mach's principle.
he's saying that he has this higher inertia, and that's by taking the propagation vector and dividing it by the speed of the electron in the material, which is very, very slow, right? So if I have a beam of
right.
electrons, I'm looking at, if I've got an electron beam in an electron tube like in an old CRT, they're running around at, I don't know, 10 to the 5th meters per second or something like that, maybe more. And if I have them running around in a copper wire, they're moving about 4 millimeters per second.
Right.
Again, that's really interactions in the material. But he's saying that there's something here on top of that that's doing that. But I'm not sure if by putting that h bar k, that propagation vector, he hasn't already done everything he needs to do to switch it into a quasi-particle. I'm actually pretty sure that he has. Switching from mv to h bar k, you've already decided you're going to look at the wave function in this complicated system. In fact, he's got a XRD, it looks like, possibly some other thing, but it looks like an XRD photograph while he's doing that. And the whole point to do that is to say, we've got this electron moving in a periodic structure, and that periodic structure is giving it extra momentum, or giving extra inertia.
I thought that inertia, that extra inertia, was entirely from the coupling between the electrons. Because it's not. I don't know what kind of coupling the electrons in a superconductor have with the material that it's moving through, but the resistance is 0. So I assumed that it was like a frictionless fluid, and your electrons were only acquiring this higher mass because when you push, basically when you push one Cooper pair, you're pushing them all, and they're very densely packed, and so there's this large scale.
Well, I mean, he's definitely doing
something
something where he's integrating over all of the current, right? He's adding up all of the current and dividing by the distance between this little bit of current and the little bit of current you care about, and so there's got to be something going on there. He's actually integrating over the entire path of it, going all the way around. But I'm not really sure how that all gets set up at some point, and I think even when he's gone to that h bar k, he's already chosen to move into this realm of the periodic structures. So it's hard for me to figure out how to get rid of this, especially since I've seen the same idea approached based on those periodic structures. He's saying we've got a coupled ensemble, and it's true. You do have a coupled ensemble, but it's just really difficult to figure out what he's talking about with this higher inertia coming from anything except that macroscopic wave function that he was talking about. That macroscopic wave function doesn't really exist without the periodic structure.
Well, this is where I'm going with this. I'm looking at the stars in our galaxy as basically test charges, mass charges, and the way that our spiral galaxy is spinning, we've got these vector potentials all interrelating because everything's in movement relative to each other, relative to the center, and all the rest. Is it possible that there's a coupling going on with the stars in our galaxy because of their motion that could explain the flat galactic rotation curves that we're seeing? Could our sun, for example, have a higher inertia because of its coupling to all of the other stars in the galaxy, And could that model this basically uniform velocity of stars in our rotating spiral galaxy?
Isn't that something that he was claiming?
I don't know if I don't think he talked about that. He didn't talk about galaxies or stellar.
But I think he was trying to say that there's no need for the dark matter, that you get all that extra mass somehow from.
No, that's where I was going with it. What he was saying is there's no need for dark energy. At the very end, he gives this teaser, and he says that with G4V, it eliminates the need for dark energy. But he never explains it. And I did a little bit of looking online to see what the heck he was talking about, if anybody knew. And somebody said that something about G4V causes the starlight of distant galaxies to appear slightly dimmer than general relativity predicts, which would explain the appearance of, I guess, greater distances or accelerations, or maybe maybe there were greater. There was a slightly greater redshift at a greater distance, but there was a perceptual artifact that created the appearance of dark energy in his theory, according to the people discussing it on like the physics stack exchange. But he never talked about dark matter. But it does seem like there might be something there. I don't know why he didn't talk about dark matter, but maybe his theory explains both.
Well, I mean, it might, but I think he was saying something about it being agnostic about all that stuff.
Oh, no, he was talking about it being agnostic about what kind of matter you have in the universe.
Mm-hmm.
His theory. Yeah, I think he was talking about that in very broad cosmological terms. I don't think he was referring to the specifics of the dark matter problem. He was just talking about the total mass energy content is the relevant factor. It doesn't matter what form it takes. He said it doesn't matter what kind of matter you have, but in my theory. But I don't think he was implying that his theory gets rid of dark matter, because I never came across that online yet. But maybe it does.
My saying that was just me not remembering that he said dark energy. That was just me misremembering something. I'm not trying to put anything into his mouth. I just misremembered what dark thing he didn't have to worry about.
Well, right, he did mention both. He mentioned dark matter in the context of there's something about his theory. I don't know. He's talking about it in a very global sense, that it didn't matter what kind of matter you had in the universe to change the mathematics of his theory, but. At the very end, there's a slide or something which says that G4V eliminates the need for dark energy also. So that was I'm just really fascinated by this theory.
And that's what I would have been talking about, because that's what I have written
Okay.
down here. Mach's principle and no dark matter.
Yeah, if you look at the video at 57 minutes and 13 seconds, or somewhere thereabouts. Yeah, at 57 minutes thereabouts, you'll see that his theory, he has a few things. He shows you the differences between the predictions of G4V and GR. And then he shows down below that it says naturally encompasses Mach's principle and cosmology without dark energy. But he never explains that last line. I really like this guy too. He's very bright, obviously, but he's very humble and he's a very gentle guy. He's in his 80s, right? So he's had this incredibly honored life. Apparently, he's been a bastion of progress in semiconductor physics. I believe that he coined the term Moore's law for the rate at which semiconductors get faster, or the CPUs get faster. And here he is in his 80s, coming up with an alternative interpretation of gravity, new math for gravity based on Einstein's early work. I just love this guy. Now I wish I went to Caltech, because I just love to interrogate him right now about his theory more. But I do believe that he's going to be coming out with some more work on this. I think maybe it was in his other lecture. Let me see, what was that called? It was called The Universe and Us, an Integrated Theory of Electromagnetics and Gravitation, which also came out last year, about a month earlier than this lecture, where I think he may have mentioned that he's working on an expanded treatment of the theory.
Okay, have you gotten everything that you thought you were looking for?
Yeah, I'm good.
Awesome.
I'm really interested to see where this goes. It seems to me like he's got gravitation and electrodynamics all worked out mathematically, that's speaking the exact same language. So if this isn't the key to a unified field theory, I don't know what will be. Because the problem with unifying quantum theory with general relativity in the past was always that they spoke two completely different mathematical languages. You're talking about tensors and Christoffel symbols, and there's all this distinctive geometrical language of general relativity that was totally incompatible with quantum theory, right? Well, now we've got an engineering approach to gravitation, so we can really, I think we're going to see some kind of major strides. Maybe we'll even understand fundamental questions like the nature of charge and be able to come up with an equation that unites electrodynamics with gravitational physics, right?
I'm not sure how this does that.
But it's a doorway. We've never been able to talk about the two theories in the same language before.
Yeah, I mean, they do spend a lot of time getting pretty close. I think there's just a couple of things that they haven't figured out how to push together. You know, the deeper you delve into that stuff, the closer it looks like they've actually gotten. You know, the more mathematical the treatment you see, the closer it looks like they've actually gotten. If we wander through and looked at, say, Z's discussion of the whole thing, it looks like there's a pretty good pace that they make up till some point, and then everything goes bad. And maybe they can't fix that. Maybe there is something fundamentally different between those two theories. But, you know, they've gone pretty far with what they have, and that's the reason why somebody can get up and talk about the spin 2 boson. Even though nobody's seen a spin 2 boson and so forth and so on, you know, he can get up and say this is sort of the thing that has to happen. So why don't you see that? Is that what you're going to see, or something like that?
Well, right, but that only has to happen if you take the geometric approach to gravitation, and you end up with these mind-bogglingly mathematical and incomprehensible theories. I mean, the only really hope that we've seen for unification of gravitation with quantum mechanics is superstring theory, right? Where you summon like 11 spatial dimensions or something, and you've got to deal with things at a Planck scale that are doing imponderable motions through a multidimensional universe. And those all and we have to figure out what topology all of these extra dimensions are rolled up into. I mean, it's just a total mind job to try to reconcile the two, right? Or there's quantum loop gravity, right? And again, you've got the most brilliant minds in the planet racking their brains for decades trying to get some kind of useful results out of these theories, or at least get them to be consistent with our observations and make predictions, right? And it's never really happened. So I just feel like this would be a great step in that direction. I want to see that full treatment of this theory, because maybe there are engineering implications for this that we just haven't seen before because we weren't looking at it the right way. Now we can start looking at fairly simple equations and problem solving for a gravitational engineering. If we want to do experimental gravitational work, this looks to me to be the portal where applied physicists can say, okay, well, we know what the vector potentials are, we've got our mass currents, we've got, you know, and this is what we were hoping to accomplish. What will it take to get where we need to go? Maybe this will help us figure out the gravitational analogy or analog to like ferromagnetism. Like if we can figure out how to amplify the gravitomagnetic field, just like a electrical current does with iron. I mean, who knows where this is going to lead? But I can't wait to see where it goes.
All right. Well, sounds good.
Well, thank you so much, Jim.
Oh, always a pleasure. Fun to watch somebody like Carver Mead talk about this stuff. So I don't know how well this is actually going to work out, but he definitely does look at things in his own way, and it's always refreshing to see somebody talk about things that way. Somebody knowledgeable and competent talk about things that way, I should say.
Yeah, he's very relaxed when he talks about a lot of physics, when he talks about the specifics of quantum theory in history, and the characters involved, and the arguments that they've had. I mean, he's just so casually familiar with the material because he's been teaching at Caltech for 40 years. I mean, he's a vastly knowledgeable guy, and there's no pretense. He's not trying to impress anybody. He just kind of plods through it, and you just get the sense of a very earnest guy trying to solve some really interesting problems. And his love of Einstein and these early papers is contagious.
All right, Randy. Well, thanks for setting this up. Why don't we end this here?